conference. So without any further delay, I would like to invite Christophe Ballif, Vice President of CSEM, to give a keynote presentation. Christophe?
Anything. So good morning, ladies and gentlemen. Thanks, Shravan, for the introduction. It is a pleasure to be able to share today with you. Can you confirm that you can see my screen now?
Yes, it's coming. Yes.
Is it here? Okay. Yeah, so I have a short time, so I will go quite quickly, as I often do with my presentations, try to give you some historical aspects of how things have developed and what are the perspectives from a research center. As you all know, I'm working both at EPFL and CSEM, who have been contributing actively to the field in the last 15 or 20 years. As you know, so historically, amorphous silicon passivation has been known for a long time, and even Neuchâtel actually in 1993 patented the rear side passivation for an heterojunction solar cell. But at that time, the Swiss government said that thin film was the future, and the IMT of Neuchâtel was forbidden to work on crystalline silicon. They had to focus on thin film silicon. So in the meantime, we all know that, as you can see on this graphic here, we all know that silicon heterojunction has been a technology driving the efficiency up. You can see with the preliminary work of Sanyo, later Panasonic, and then Kaneka, that actually already in 2015, there was this barrier of 25% superseding the high temperature processes. And then Kaneka with the IBC went even one step further with 26.6 or 26.7%. And if I try to make a kind of historical map, I try to put a few things here, how things have evolved in terms of which companies started some mass manufacturing. You can see a lot of known-name, of course, Sanyo, but then there was Sunprim, even applying plating at some times. A few companies in Europe, RRC, and now, of course, as we know, a lot of companies in China and several companies in Europe. There have been a lot of pilot lines at many institutes, but also at many industries, a lot of interest from makers, and a lot of synergy with some fields such as flat panel display, especially with respect to PCVD and PVD tools. And of course, many research labs that started to work more and more on the technology, including in Europe, IMT, CEA, HZB, and later after its foundation, CSEM, in parallel, CIMIT in China, and more joined the race. So from the perspective of Neuchâtel, of course, for us, what was a triggering point is that in 2002, 2003, people were thinking there was some kind of black magic in passivating solar cell with amorphous silicon and making it work. It was very hard to get good fill factors. And for us, I still remember in 2005, we found the way to work on textured wafers and to achieve VOC with PCVD and PVD. It was really a success and a landmark point. At that time, Panasonic or Sanyo were focusing on other processes, with in particular hot wire and ion plating for the TCO. And in Neuchâtel, we followed the road, working jointly with, in particular, the Meyerburg group, collaborating with CEA, which leads to also first delivery and turnkey lines for heterojunction solar cells. And of course, you know that now Meyerburg is also having production facilities in Europe for heterojunction solar cells. So if I try to have a look now on what happened in the last 4 years, I want to refer to the second international workshop on heterojunction solar cell, which took place actually more than 4 years ago in Chengdu. At that time, we were seeing things such as we think that 23-24% solar cell can come in production. There could be a potential to go to 25%, and many other things that would be possible. Still, with some issues, in particular, the CapEx was still quite high. There was a lot of space consumption, of ITO consumption, maybe some question about reliability, and with a need for more studies. But at this stage, I mean, it was really at the mostly sub-gigawatt level, except maybe for Panasonic, but it was still relatively small. So the conclusion was that heterojunction was ready for mass production, but that it was in competition with PERC, which is interesting because today, thanks to the efficiency improvement, then nobody is speaking about the comparison with PERC, but really more with TOPCon. So the question is, where do we stand 4 years later after this workshop 4 years ago? And is heterojunction really started to jump? And I put here a picture of a ski jumper because when I was young, I was also doing ski jumping. So as you all know, there have been tremendous improvement in manufacturing technologies, and now with a lot of new actors, mostly in China, including Wasan as a leader, and all names that you know here, plus some companies in Europe such as Enel, Meyer Burger, and possibly some new companies with, at the end of the year, we estimate something like 50 gigawatt really installed and able to produce this capacity. It is not production. And if you have a look at various reports, you see that there are announcements that would correspond to something like 110 to 117 gigawatt, even though it's still very question whether these projects are realized. So if I try to summarize for the very important things that happened in the last 4 years, the first one is efficiency. Of course, I'll come back to that. There have been now more and more teams and pilot lines and production lines that can go at 20%, 25% and other. There have been much higher performance equipment in terms of throughput, also in terms of cost. Now we're talking about $37 million of CapEx for the equipment in China, which is strong reduction by a factor more than 2 in the last 4 years. There are opportunity with raising the efficiency with also tools that can make nanocrystalline layers with a high productivity. There are more and more solutions to save silver with multi-busbar interconnection, sometimes busbar less. There is something that's important also in terms of trying to fight on the cost, which is this ingot usage, especially when you consider like the large wafers. And if you work with half cells, then now you can also use these parts from the square, or you can reuse this part to make wafers. You don't need to remelt like almost 1/4 of the ingot, and this helps for the cost. And you can keep a thickness of around 110 to 115 micron against 130, maybe for 135 for TOPCon lines. So those are all things that have been very positive. And if I maybe come back to the efficiency, of course, we have seen this drive with first Japan, then some good results also in Europe, and now with a lot of excellent results from many Chinese pilot line and even production in some cases with record efficiencies up to 26.8%, even though with layers that are very transparent that might bring a lot of challenges also in terms of stability. But still now you have a lot of results certified at Fraunhofer Institute or ESFH with over 26% efficiency, at least at the pilot line level. So this is all very interesting and very good. And this has been driven by a certain number of factors, but in particular, this famous improvement in the fill factor. As you certainly know, you can reach typically for 130 micrometer thickness voltage above 750 millivolt. But also if you have a perfect passivation, perfect device homogeneity, and you minimize your edge losses, then you are entering into a regime where your fill factor is somehow increased artificially by the Auger effect. To make it simple, you have more Auger recombination at open circuit voltage, less at the maximum power point, and this can drive the fill factor up. But in order to do that, you really need to have a very, a perfect passivation and very homogeneous passivation. And of course, to have such high fill factor, you need very low contact resistivity. In particular, you can use nanocrystalline layer to help for that. And narrow line printing with high conductance will also help to get high current, a little more VOC, and low resistive losses. So, and what we've seen, as the Shravan mentioned, is that now you start to have commercial modules that come with efficiency in the range of 22.5 to 23%. Companies who have both TOPCon and heterojunction in the pilot line still see a possibility to gain 15 to 25 watt, comparing heterojunction with TOPCon. And we've seen recently a few very impressive results, in particular from Wasan with a certified module at 24.16%. You will see that in the future talks, of course, also of Tongwei, slightly below with plated copper contacts. So very impressive results, also remarkable result by Reason and ACOM close to 24%. So there are several prototype modules. These are not yet really commercial efficiencies. And this is all good, but of course, the others are not sleeping. And you have, of course, heard that Jinko is also showing very nice results with proto modules of 24.7%. So the race is still open for these efficiencies. Of course, there are other options for the heterojunction. So you have also the IBC configuration with here the record of Kaneka with 26.7%. And with also nice result for many other Japanese groups and Swiss entities. And of course, there are new things happening. And in particular, there have been some results from GS Solar, which have not been certified in the European Institute, but at least that could show in the Chinese certification full cell efficiency apparently above 27%, and the TÜV certified modules with 24.88%, which is also quite remarkable. So it looks all very good in terms of efficiency and what you can do. But this last results here in terms of IBC solar cell, of course, does not fully address the problem of large solar parks where bifacial modules are in very high demand. So now maybe a special note in terms of research center, what we see is that to do research, to understand the limitation, to go further becomes very hard for the research group. It's, you know, all the money is flowing now to perovskite. It's not easy to publish on that topic. And of course, when you are working with small volume, small samples most of the time, it's a real challenge to improve things further. And just to give you an example of at the EPFL laboratory here, by tuning and playing with all this knowledge of the thin film silicon, we have been able to bring the efficiency by making a lot of multi-layer and so on to 24.44% on 2 by 2 square centimeter, which is actually a very good result for 2 by 2 square centimeter. But then the air is extremely thin to try to go higher in efficiency and maybe to prove that some other treatments might improve the devices, or at least people would have to trust that you cannot always work at the 26% level when you are in research center, and all research centers are making this conclusion. But the risk, of course, is that you still need to have knowledge on this device, and there should still be some support to try to understand these devices, which are somehow still complicated. You're dealing with other kind of defects and interfaces than with standard crystalline silicon technology. Now, of course, in terms of challenges, there are still a few one. The major one for me remains indium usage. So depending on how you calculate, you will have indium available for 40 to 60 gigawatt if you use full layer thickness. You can recycle part of the indium, of course, the one that is lost. But even though we know that there are a lot of processes where you can divide by 2 or by 4 the indium usage, every time the results are a little low in terms of efficiency. And when you're in the efficiency race, it's still not obvious that company will change from ITO or variation, but indium containing. So here there is still some further works that need to be done to bring that to bridge the small 0.2% gap that you could have, for instance, by using tin oxide at the rear side. So indium remains a challenge. A second challenge is still metallization. So now TOPCon has also made a lot of progress with results depending on the companies. Some claim 10 milligrams, some other more at 14 milligram per watt. Heterojunction with 0 bus bars or high number of bus bars can come to similar level or even lower. there is, of course, all this emergence, and I think we'll hear that from fusion from the silver copper paste that allows to save on silver in some specific conditions, but which brings with additional complexity and sometimes also sensitivity to the environment. So here we see a lot of progress and potential to switch to more and more copper containing paste. Even some paste could be with much higher copper content. Plating would be a fantastic option. It has been challenging to develop mass production tool, but we see also very promising solution that would come quite quickly on the market and would at least partially solve the silver problem, knowing that, you know, it will be a speculation market. There is enough silver to make 1 terawatt of PV per year, but if investors think that the price of silver go up, it could go up by a factor even 10, who knows, and then it would be almost 10 cents per watt for most technology, and then the companies that use less silver and, for instance, plating would have a strong advantage. And for instance, at CSEM, we have also developed a process that contains absolutely no silver, and by working with narrow line printing, with the technology of UT-Light, with copper seed layers, and then with plating reinforcement, we were able to show very nice line widths with a relatively easy process where you make just the masking, the self-masking by depositing a dielectric on the TCO, and you can also save on the indium content at the same time. The final big challenge is about reliability. We made a lot of analysis to check about the available data, and what we found out is that for mostly one technology, because it was mostly Panasonic basically delivering to the market, the performance loss ratio were between 0.5 to 0.7% per year. But if we eliminated the dubious data, it was more like 0.8%. But some systems were at 0.3%. So, which means it is a little less good than the standard crystalline silicon, but some systems perform very well. And there have been more and more awareness on that topic, but maybe not yet enough. And we propose a series of mitigation measures on these topics. So things that have also been known, and in particular, it has been shown by Panasonic, is that there are some sensitivity to UV degradation. You need to pay attention to how you make your layers. You need to use some UV blockers. We have seen also the emergence was already tested a long time ago by CIC and Nito Denko down converters. We'll hear a presentation by Carl from Cybrid this morning. Down conversion foil offers an important possibility to mitigate some of the losses and keep still highly transparent layers at the front. So but attention has to be paid to that. But there are a few very good things for heterojunction. And for instance, we spend quite a lot of time to test, for instance, acid-acetic resistance of heterojunction. And we found in many testing that heterojunction are actually more resilient than, for instance, PERC and ALBSF solar cells to acetic acid degradation. So I'll refer you here to a paper. We also found that EVA can really bring a lot of problem in heterojunction, and even in damp heat, because actually we can have sodium migration through the EVA in a pure damp heat test, providing that there is some moisture at the same time. And actually, when we use glass and edge sealant, we can make modules that are even in dark and without illumination that are completely resistant to PID testing. So there are a lot of things where sensitivity can be higher for like PID if you don't pay attention to the encapsulant, but you have also mitigation measures that can make things extremely good. And there will be a new model published on that quite soon. There are several data that show actually good field performance for heterojunction, but there are also some data that are not so good. And I think here it's an invitation to the community that really data are published to validate also the high potential energy yield. And of course, there are really things that have to be made in order to ensure a good stability of the devices in terms of encapsular, of possible edge isolation. Pay attention to the thickness of the layers. Transparency and higher current can be good. It's necessary for the efficiency, but can create more interface defects. And that's why here heavy testing and serious analysis is required. So to conclude, for the future, of course, it's always difficult to predict it. I still think that there are a lot of industrial efforts. I still think that some of the basic things with respect to understanding, for instance, better silver copper paste, making progress on that topic is very important to really come with good solution for using less indium, because if the market would go to 100 gigawatt, then there would be serious issues, or you need to get ready for that. We need more data for the reliability and the energy yield. Then you can start to exploit all the small gains that you can have thanks to the very high open circuit voltage, still a better temperature coefficient, low illumination behavior, better bifaciality, better ingot usage, thinner wafer, high yields. Then it gives a chance to compete with TOPCon, but it is a tough race. And anyway, TOPCon will be the dominating technology. There will not be 800 gigawatt of the current heterojunction technologies. Of course, work to push the efficiency jointly with the reliability to the limit. I think it's good to have technologies that compete. You need several technologies to stimulate research, innovation, and heterojunction company can also market themselves with alternative product to mainstream technologies. And of course, there are these upsides potential with IBC. And of course, also this very easy implementation of heterojunction into perovskite, where in particular, all the front side TCO and this, anyway, you need them for the perovskite, but then you can kind of suppress them for the heterojunction. So with that, I would like to thank you for your attention and wish you a good follow-up for the conference.
Thank you, Christophe. Thanks a lot. Do you have time for one question? Christophe, do you have time for one question?
Yeah, of course. I have a lot of time.
Oh, okay, great. Since you said this. So, yesterday there were several slides showing the theoretical potential for heterojunction and TOPCon. So what I learned yesterday is it's the theoretical potential for heterojunction is at 28.5. So what is the practical limit you see for the efficiency of heterojunction? You are working on so many things, and if you connect all these pieces.
Well, then we just have to pay attention to efficiency. Although we have seen that it depends a lot on how you measure your devices, and there are a lot of solar cell measurement that tends to overestimate the efficiency, in particular by erroneous measurement of the field factor. And what counts in the end is what you have in the module. So if you speak of an ESFH efficiency, I think that practically, if you consider it depends if it's a IBC or if it is a front side contacted. So I think we'll bring front side contacted maybe in the range of 27%. Longi has already demonstrated it, but practically, I think all people who work in technology know that maybe you'll make a record with 27.5, then maybe IBC might have a record at 28%. Then whether this is applicable to industrial production, it brings, you can add a lot of layers, it brings complexity. And the question is up to which level of complexity you can go. But let's say we could target things such as 27% for front side and maybe 28 for IBC. That would be my guess if you would give me a few $1 billion to develop these things.
Hope I have. Good. Thanks a lot for your presentation. And if you have time, there are, I think, a few questions here in the chat window. Would be great if you have time to answer them. Meanwhile, I will continue with the session.
Okay, thank you.
Thank you.